Our next section is on graphing, so I'm going to walk you through how to plot a graph and then also some of the different graphical variations that you're going to see this year in physics. So let's get started. There are two variables we are going to look at. The independent variable, which is the one that you, the experimenter, controls directly. It will be plotted on the x-axis, which is the horizontal axis. The other variable is the dependent one, and it changes as a result of the independent variable, hence it depends on it, giving it its name. This one is plotted on the y-axis, which is the vertical one. There are a few helpful hints to remember when you're plotting line graphs. You want to identify the independent and dependent variables first in your data, and then determine a range for the independent variable to be plotted. Decide whether or not the origin is a valid data point, and we're going to do labs where definitely the origin is a valid data point and also when it is not. So it's going to be important that you learn to determine the difference. Fourthly, you want to spread out your data as much as possible. Let each division on the graph paper stand for a convenient unit. So it's really helpful if you go in multiples of, say, 2, 5, or 10, something that's easy to count by. And it's really important that these divisions are the same and that you spread them out evenly. That means there are no breaks in the graph. Also, this means that each interval along an axis must be represented by the same multiple. So, for example, you cannot let one section of the graph paper be in multiples of 2 and then later on down the road count by tens. So go ahead after you've determined your scale to number and label the horizontal axis. So you also want to include units for this. So when you're taking your data, whatever your independent variable is, you're going to label the x-axis with that variable and also the units. Then you'll repeat these same steps for the dependent variable. Next, you're going to draw a best fit straight line or smooth curve that passes through as many data points as possible. Sometimes this is called eyeballing your data because you're giving a rough estimate for a line that looks like it best fits the data points that you have. And it's important to remember that this is an estimation. It's like an average of your data points. Do not, under any circumstances, connect the dots. We are definitely going to practice drawing best fit lines on our graphs because that's something you're going to see come up in almost every chapter that we do. And then finally, your last step is to give your graph a title that clearly tells what the graph represents. If you're not sure what that would be, it's always a safe bet to say y versus x. And don't simply put the letters y and x in there. You want to substitute those with what is actually plotted on the y and x axis. But when you see instructions to plot something, it's going to say plot one quantity versus another quantity. The first quantity listed will be on the y-axis. The second quantity listed after the versus part is going to be on the x-axis. We will follow that rule all year long. So for example, if I wanted to say plot distance versus time, in looking at that, if it said distance versus time, the first quantity listed, in this case distance, would be plotted on the y-axis. And you do want to include units, so remember that distance should be measured in meters. And you can use parentheses, I just use brackets out of habit to list my units. And then time would be on the x-axis, and remember that time is in seconds. So again, if you see instructions in a lab to plot one quantity versus another quantity, the first one listed goes on the y-axis, the second one listed goes on the x-axis. Next, I'm going to walk you through some of the graphical variations that you're going to see this year and give you a rough sketch of what those graphs should look like. The first one, and probably the most common one that you see, is going to be direct or linear. Sorry, that wasn't a very straight line. I meant to underline that. So direct or linear. When you see a direct or linear graph, it's going to be a straight line. It might go through the origin and look like that, or you might have a line that has a y-intercept. So it might look like this and actually cross somewhere along the y-axis. In either case, the equation for a direct or linear variation, you would have the equation of your line be in the form of y equals mx plus b. M represents the slope, and I'm guessing you know how to calculate the slope. You would simply plug in the change in 2 of your y values divided by the change in 2 of your x values. And then b in your equation represents the y-intercept, or where your line crosses the y-axis. If it crosses at the origin, you would simply say plus 0 or leave that off and just have an equation that says y equals mx. In either case, if one variable increases, the other variable increases as well, and vice versa. So if one variable decreases, the other one decreases. Both of those are indicative of a direct or linear variation. Our next relationship is called inverse, and equations for an inverse graph would follow the format of y equals something over x. So if one variable increases, the other one will decrease. They're going to have the opposite behavior of one another. On a graph, you're going to get a kind of curved line that looks like this, and this is called an asymptotic approach. What that means is either end of your line would approach the axis, but it's never actually going to cross over into another quadrant. So all of your data is going to be locked into this one quadrant up here. Our third variation is called parabolic or quadratic, and I know some of you guys may have drawn parabolas in your math classes that went on both sides of the y-axis. For us, typically we will only have things that deal in this quadrant, and usually the origin is a data point for us in a lot of our labs for physics with a quadratic or parabolic variation. Your equation for this type of graph is in the form of y equals some number, represented by an a here, and then times x squared. It's the x being squared that makes this easily recognizable as a parabolic or quadratic variation. Our next relationship is called an inverse square variation, and the formula for that looks like this. It's y equals, there's going to be something on top in the numerator, and then in the denominator we're going to have x squared. It looks similar to an inverse graph, but it's a little bit more steep. So it's shaped a little bit more like this. Your sketch is going to be following closely to each of the axes, more so than the inverse variation would. So there's not that much difference. The important part will be to look at your formula to see the difference between inverse and inverse square. And the last graphical variation that you would see in physics is going to be y equals and then just some number. So if you were to plot that, it would simply be a horizontal line. This one is actually pretty rare, but we are going to have a couple of instances come up this year, so I'd wanted you to be familiar with that. That concludes our section on graphing. We're going to spend a few days in class doing various types of labs so that you can see each of the types of graphical variations, and we can practice with those, and then you'll be able to recognize them more easily as we go throughout the year. Thank you for watching and have a great day.